tricks. So one of them is burning glycerin for process heat, which I don't have a huge amount of new information about, but it's something I've fooled around with a little bit. Mostly I'm going to show you just a very small PowerPoint with a few photos of stuff that you may have already seen on the web. Then we're going to launch into some physical and chemical processes for working with glycerin to do interesting things with it before you actually burn it in Dale Turk's waste oil burner. And it's a concept that's kind of new. It's been coming around the InfoPop Biodiesel forum and some other homebrew forums recently. It's sort of about using glycerin as a carrier or using glycerin as a way of removing some substance that you don't want from your reaction or forcing separation of something from your reaction. Various different uses that people have been tinkering with the last few months. We'll talk about testing for soap. We'll talk about what soap is, how to break it up, what to do with the result. We'll talk about acid catalyzed esterification, and we'll talk about ways of recovering more biodiesel out of your waste glycerin byproduct. So,
no ethanol?
I'm sorry?
No ethanol?
And ethanol. Sorry. So that, in fact, that's going to be that's topic number 2. So real quick, I want to do a real quick little slideshow of just photos of a homemade waste oil burner that some of you may be familiar with already. This is a homemade waste oil burner invented by a guy in the Midwest named Dale Turk. So typically we call them Turk burners after the guy who I'm not even sure plays with them anymore. And it's a simple way of creating as complete of a combustion as you can out of a waste oil or out of glycerin or out of biodiesel or waste vegetable oil by using a blower and a device that forces air at a burning pool of liquid. So real quick, concerns about burning glycerin for fuel. It does work. It's glycerin and waste vegetable oil both come with some health concerns if they're not burned fully. This is actually true of a lot of other kinds of fuels, including wood stove, wood smoke, cigarette smoke, things that smolder, generally produce a whole bunch of intermediate compounds on their way to being heat and water vapor and CO2, which is that they produce compounds such as acrolein. That's the one that really gets associated with vegetable oil and with glycerin the most. And so a lot of the time when you start talking about using straight vegetable oil in a vehicle, you'll hear people come up with, oh, but what about the acrolein? You'll hear this concern. It doesn't really appear like it's actually that much of a concern in terms of straight vegetable oil use, by the way. But it comes up a lot in regards to boilers. It's one of the several testable toxic substances that will come out of your smokestack on a boiler. And as far as I can tell, the main reason why it comes up a lot in regards to vegetable oil is that it's been extensively studied as a byproduct of smoldering during cooking. So it's very well known that when you have vegetable oil that burns, that reaches its smoke point and begins to smolder, for example, in a frying pan that's running too hot, that is a lung carcinogen, I believe. And it is a substance that will break down in the atmosphere, so it's not actually like a persistent pollutant, but locally in the immediate area of the combustion, there are concerns about, or a lack of combustion, there are concerns about what happens if you're not achieving complete combustion when your starting material is something like vegetable oil or glycerin. Basically, combustion 101. Fuel oxidizes very rapidly and turns into heat, CO2, and water vapor if you've got the correct conditions. So correct conditions are basically as much oxygen as it needs. And that can be hard to achieve if you are trying to cut down the amount of heat you're getting out of a burning pool of fuel. So in a wood stove, we're creating optimal conditions for pollutants such as acrolein. And the reason why this happens is that in a wood stove space heating situation, we're typically trying to kind of dampen down the amount of oxygen going to the fuel. You're not achieving complete combustion. The whole goal of why people do that is that they're trying to make the log last and they're trying not to overheat the room that the wood stove is in. And those are all known reasons why wood stoves, for instance, are a very poor heating device from a pollution standpoint. They don't burn the fuel all the way down to being CO2, heat, and water vapor. Same thing would happen if you were running some kind of vegetable oil or glycerin as a fuel in that kind of a setting where you tried to get a smaller flame. So tried to control the flame by cutting down the amount of air that you're giving the combustion event. So basically the short, the lesson to take from that is that you cannot burn vegetable oil or glycerin without anything other than complete combustion, like an excess of oxygen, so that you know that you're going to get everything burned down and you're not going to end up with pollutants in the smokestack, coming out of the smokestack or coming into your immediate area that are known human health effects concerns. So generally, for space heating, you know, what that generally points to is that you would have to burn a very hot flame using your vegetable oil or glycerin, and then you would have to have a way of capturing that heat in a liquid storage medium. So for instance, a hydronic system where you've got a burner that's running, you know, as hot as it needs to achieve combustion, and then there's a heat exchanger that water is running through, or that glycol is running through, that collects that heat and allows you to have an easier way to control where it goes. So basically, a typical example is you know, a boiler that heats some sort of a storage tank of water, and then that water is being pumped through your house using heat exchangers or radiators in your house. For biodiesel process heat, the same thing applies. You would not, if you were working with a fuel that was easy to combust, then perhaps you could have something like a gas, you know, propane heater underneath your tank of vegetable oil that you're heating up for biodiesel processing or heating up for dewatering purposes. But if you, and in the case of something like natural gas or propane-fired boiler, you'd be able to turn down the heat because it's a lot easier to get complete combustion of the gas than it is of our vegetable oil or glycerin liquid fuels. But the best way to achieve control of fuel of the vegetable oil or glycerin liquid fuels in a burner situation for process heat is actually to go with a hydronic system as sort of an intermediate carrier for the heat. Burn the fire as hot as you can, make sure you achieve combustion, and then move the heat elsewhere and use pumps and a sort of hydronic controllers to get it to go where you want it. Steve?
You want the burn to be over?
There's not. There don't have data on like what the temperature actually is supposed to be. I think that really it's not about what temperature you achieve. It's about I think that's going to be relative to the exact combustion conditions in your burner.
I understand it's around 1,200 degrees though.
Okay. There's a vast number of rumors on the internet that everybody loves to attach a number to this. I haven't actually been able to document where that came from. And I think it might actually be hotter than that if you're talking about Fahrenheit. But I'm not sure that just measuring temperature is going to give you the assurance that you've got complete combustion, because I think it has a lot. There are other factors at play. But basically, the lesson is the more oxygen you give a fire, the more complete the combustion is going to be. So essentially, the goal of a lot of waste oil burning is to flood the combustion chamber with as much air as it'll take. So there's various ways that waste oil burners achieve this. And what they typically do is that they atomize the fuel itself into very small droplets and allow it to burn through completely surrounded by air. Often that involves doing something like having an air compressor that is helping to atomize fuel into small droplets, or there's compressed air somehow going into a stream of fuel coming out of a nozzle under high pressure. That can be kind of a hassle to keep maintained. And a diesel engine is actually kind of a good example. Diesel engine injectors are a good example of that kind of a burner. We achieve complete combustion, or at least we try to, by having high pressure spray out of injectors. And any of you who've run straight vegetable oil or had experimented with diesel secret type of solvent thinning processes might know that it can be hard to keep your injector nozzles from clogging when things go wrong with your fuel. So there's, or when something goes wrong with temperatures in your combustion chamber in your engine, for example. So I don't like atomizing burners. And actually another example is I think the typical home heating oil burners that you see in some parts of the country are also a nozzle that sprays fuel under 100 psi types of pressures, not too high. And you're trying to get the home heating oil to spray into small enough droplets that it will burn completely in the time that it has in the combustion chamber. There's a couple of other approaches to burning fuel. One of them is gasification, which John Bush may have talked about privately to some of you, a project that he's working on. That's more about solid fuels, correct? There's not a way to make that work with liquids, right?
Listen to, I don't really know the details. I don't work in that department at my company, but it's, it's more of a thermal breakdown, I believe, is like pyrolysis.
Mm.
It's actually not a combustion process without oxygen. No oxygen involved.
Yeah, so but what you're doing is generating, yeah, gasification, you're generating a flammable gas, which is very different than taking a liquid fuel or a solid fuel and making it into particles that then interact with oxygen.
Absolutely, yes.
The type of waste oil burner that Dale Turk came up with is actually a vaporizing burner. So here, what we have is a combustion chamber on the inside of this pot. This is kind of a bare bones version. I pulled that picture off the internet. I'm not sure whose burner that is, but it's pretty typical. And essentially what we have in there is a central pot that you can't see from the flame is coming out of. Basically a big tube with a bowl at the bottom. And there is fuel sitting in the bottom of the bowl. The outer shell, which in this case is a propane or helium tank, basically forms a way for air to surround that inner bowl or cylinder full of fuel. And the inner cylinder is only partially full, it's only half full. Above the level of the fuel are a whole bunch of little holes, and the contraption coming off the side is a blower, and this is actually a fairly low power draw kind of a blower compared to running an air compressor. So what's happening in this photo to get that nice flame is that you've got a lot of air going into this restricted space between the inner chamber and the outer shell. And there's air holes that allow that air to go into the inner chamber. So essentially air is able to blow over the surface of a pool of burning fuel. You have to get the fuel started and started burning some other way. We usually use the much derided throw a burning rag in method. Currently, PMOP Biofuels has an engineering intern who sneers at that horribly as being terribly unprofessional, but it does work. And or having a wick of some sort that starts your pool of fuel burning under under the normal amount of oxygen that you have in the air in the chamber under normal pressure. Once it's burning, it will heat up the surface of the pool of fuel, get it hot enough that it begins to boil. And then you kick on the blower. So it's not compressed air, it's just a blower. And once that air starts coming out into the pool of burning fuel, you begin to boil the surface at an even hotter temperature, and essentially you're creating vegetable oil vapor or glycerin vapor. It's like a steam, the steam to water, same idea. It's boiling vapor that becomes easier to burn completely than if you had taken the fuel and put it through a waste oil shop heater or a home heating oil type of a burner that atomizes the fuel. Yes, sir?
Can you give us a frame of reference for boiling temperatures for glycerin or vegetable oil?
600F-ish, I believe. Someone correct me if I'm wrong.
Closer to 300C.
300C, yeah, what is that?
300 times 220, 660.
660, yeah.
Okay.
So, and then that's actually very close to, that's actually close to its decomposition temperature. So, but it will, it's not that high. So once the burner is going, once the air is actually going, what's really doing all the burning is just the boiling vapor. There's a pool of liquid. You can actually sometimes see through the flame and see that it's bubbling and boiling, and then the burn is happening a little bit higher. So you see a nice swirling flame coming out of your air holes where the air is hitting this glycerin vapor. And you get fairly good combustion. It's real, exactly how good it is going to depend on the exact burner design and how much air you have relative to the size of the pool of fuel, how much heat you're robbing from the whole process. Nobody's done emissions testing on these things yet, but it does appear that they get pretty darn hot. So there's just a few photos. This is, I think, Dale Turk's one. He encased it in a wood stove, so he's able to, I'm guessing that that's an air pipe. I'm not sure where exactly his blower is, but this is a good way to get space heating out of it. It also makes it considerably safer. Big drawback of these guys is that, hang on a second, the big drawback of these burners is that they're really hard to control. One thing to note about them is that no pictures that are on the internet really do justice to how hot and how bright they get. So there's me with cutting goggles on so I can see what I'm doing, and if we weren't wearing them in that particular situation, everybody that was present at that point came away with seeing spots pretty badly. Like it was a pretty bright flame. Real hard to get a digital camera to do that without some, to really capture that without doing some good processing. But that's basically what the inside of these guys looks like. It's a tube or pipe with holes. The more holes, the better. It really depends exactly on what your air source is and how much back pressure it can handle. But this sits inside of an inner, or of an outer shell, and your fuel level is below the level of the holes. So a lot of the challenges with this really are about how to control the liquid level inside the burner. They're typically used as sort of a batch system where you fill them once, you get about 20 minutes to an hour of burning, depending on the size of the actual unit. You let it cool down, you refill it, you do that all over again. I haven't done any calculations on how many BTU an hour you get with different fuels doing this, because again, it's all going to depend exactly on how you design your unit and what materials you use. But and they don't have to be made out of propane tanks. All the ones that I showed are all propane tank, Freon tank combinations. But ideally, you would probably build it out of stainless steel pipe or something that would be more durable at the high heat than these scrap-based ones. But they're a really easy way to turn glycerin into pretty tremendous amounts of process heat. And it does appear that it will give you pretty complete combustion from flame color, flame stability, amount of residue left, lack of smoke. If you burn this thing in the daytime, you basically see wavy hot air. Jason?
I was just going to say that some research I've done on IRS shows that they will pay a 50-cent per gallon tax credit. It's not a tax credit, it's just another credit, excise credit, for using vegetable oil as fuel.
In a business, in which kind of setting?
Well, even in the personal setting, it wipes out your road taxes, but if you're not doing it as a
Wow.
business, for a personal setting, for on-road fuel, then yeah, it has to be a business.
That's
What we do is take our waste and burn it and we get paid.
Yeah.
That's pretty amazing.
How's that sustainable?
Awesome.
Well, what's unsustainable about it, sir?
Well, I mean, it seems strange to encourage people to burn something.
No,
Why?
it says a replacement for petroleum fuel.
Okay, so how do you show proof of, I don't understand what.
I can talk about it in my presentation later.
Okay, great. Jason's doing a next presentation, which is the radar is not so high off the ground, and he has researched things like that. So that's, but from a sustainability standpoint, actually, complete combustion of material that came from a bio source to begin with is not any more or any less sustainable than making biodiesel or using vegetable oil in your diesel vehicle. Other than the methanol content, I suppose. So tests that I've done. This will burn. Sometimes you'll hear people claim that what is burning is actually the methanol or things like that. You'll hear quite a lot of questions about whether this works with methanol recovered glycerin. It most certainly does. I actually found it easier to light for some reason with methanol recovered glycerin. Turk burners will leave behind a mineral residue, ash, if you have worked with unwashed, if you're burning unwashed biodiesel or if you're burning glycerin that has soap still in it. Also, they appear from other people's reports to be sensitive to water. So there are problems when you've got pre-washed glycerin that comes from a biodiesel reaction where you used a 5% water pre-wash. So that may be a problem. If you're doing methanol recovery anyway, it may, and you've got a source of cheap BTUs, which with one of these units you will, it may be worth actually dewatering that glycerin after removing methanol, which is probably pretty energy intensive, but again, you're using waste glycerin for heat anyway. From what I've been told by people who do use this kind of simple system for process heat, you'll still produce much more glycerin than you actually need, so you've got something to work with to do things like dewatering, is my understanding. All I've really done is play around with them and try to characterize what fuels they work on and what problems that brings up. But there are people who've used them for dewatering vegetable oil by boiling, which is generally not a very safe practice for other reasons. But there are situations in which you have to do it. If you're off-grid, you don't have a source of propane, natural gas, or electricity, you're probably going to be dewatering your oil or heating your oil by putting a fire under it of some sort, and this is one way to do it. Obviously, the safer way to use the heat from a waste oil burner is to turn it into, store it in a hydronic system and then move it around with, with heat exchangers in a more remote location. There's a couple of, these are very poorly documented on the web actually. There's greentrust.org, which is, as you can see, very old. This was an article in 2000 that they put up. They were one of the first biodiesel websites out there. I think they were called something else at that point, but that's about how old this whole thing is. There are plans on there for how to build the propane tank one. The idea is basically, air holes above a puddle of liquid, and then figuring out some way to keep that liquid at a certain level is the big challenge with them. There's a pretty good write-up at someone's personal website here that has some good photos of some novel ways that another gentleman built one. Sir?
You might want to look at the 1941 military stove, tent stove.
Yeah, that's a Babington, that's an atomizer. They're
Well,
heating up
no, it's not. It's a puddle.
Oh, okay, I'm really sorry about
It
that.
has a carburetor, quote, carburetor that keeps your cool
Oh, yeah,
level.
yeah.
It would just need added force.
Yeah, so some simple ideas for flow control is that a couple of different things that I haven't tried or have either talked to or seen other people do. Float control. Most likely you're not going to stick a float into the boiling pool of glycerin and soap, right? That's a really nice situation for gumming up sensors, floats, etc. Or, you know, most materials can't handle the temperatures in there anyway. So you're going to probably want to do your Turk burner where you're, you know, have a heat exchanger above it of some sort that captures the heat. And then whether that's a jacketed, you know, whether it's encased in some sort of jacketed wood stove type of a setting, or whether you have a coil that liquid is moving through. Be aware that they will melt, they will reach temperatures high enough to melt aluminum and so forth, so you need to make sure that if you have a liquid heat exchanger in the flame, you have liquid moving through it. I think that ideally, what the ideal kind of small-scale homebrew application of this would probably be to build a small enough one that you can stick it underneath a natural gas water heater. That would be a pretty nice wood stove that already gives you a flue, ways to pipe the exhaust out to another, you know, the great outdoors and so forth. Anyway, float control. Your goal is to keep the liquid level below the level of your holes and still be able to reuse the thing, refill the thing. So most of the designs that people have either experimented with or proposed all have to do with having an external level sump that actually has your level control device in it. So if you were planning on using a float switch to control level, you probably want to stick it in a pool of cool liquid external to the burn chamber. One of the proposals that's floating around is that none of us have really tried out is using sort of a chicken water type of a design, where it's a sealed system or sealed on top system that has only one outlet out from the bottom, and this should dispense at an even rate into you know, and be regulate this liquid level based on how high the output is. Lots of different ways to achieve that. Another thing I want to briefly touch on is that more ideally, this would not be steel in the combustion chamber. Ideally, you would use something like refractory cement or some sort of a insulated material that does not rob heat from your actual combustion chamber. And the idea behind that is keeping temperatures high enough to get complete combustion. A bunch of us in the Sanford, North Carolina area recently saw an experimenter down there, I believe on the InfoPop forum he posts as Bubba NC. He's got a very nice backyard metal casting forge that he built based on the Turk burner concept. So in his case, instead of having a boiling pool of liquid, he's actually shooting liquid by what he's doing it by way of, or he's dripping liquid into a very small burn chamber bowl. He's also shooting air at it through a pipe. It's sort of a similar idea, except for that he doesn't really need this surrounding jacket of air, and he doesn't need all the small holes that the Turk burner propane tank versions require. He essentially has a big chamber made out of refractory cement. Inside it is a real small bowl that the boiling and the burning actually happens in. This is easier to keep heated so that it boils the liquid and causes it to turn into glycerin vapor or vegetable oil vapor. And then the rest of the unit where the burning actually takes place, so you know, you've got vapor rising and then you've got air coming in out of a pipe, and the actual flame begins to burn higher above the liquid level. But he has the chamber encased in refractory cement, so he actually keeps these critical temperatures high. And the bowl is real small, so it's a lot easier to get that small amount of liquid to boil and completely turn into, you know, having a smaller amount of liquid and more air gives you slightly better burning characteristics. And so instead of having lots of holes of air inlets, he just has one large one. So this is something like a 2-inch pipe or one and something inch pipe with a blower on the end of it, and his fuel is just sort of coming in and dripping down into this bowl and vaporizing pretty immediately. There are a lot of old waste oil burner designs out there that are based on the drip pot method. So if you look at drip, if you Google something like drip waste oil burner, you'll find a lot of different ideas to play with. But the main thing to kind of come away from this with is that the reason this achieves complete combustion is that you're burning in a real serious excess of oxygen, and you're able to get the glycerin or the vegetable oil to come in contact with all of that oxygen by turning it into a vapor, rather than droplets, or rather than just have it try to set a pool of fuel on fire, or glycerin bricks and sawdust, for example, on fire, which is another way that people do it. John?
Have you noticed a relationship between the starting temperature of the glycerol and how long it takes to get going and burning completely, or does it just get going pretty quickly even when it starts off pretty cool?
It depends on the exact burner.
Okay.
Yeah, I'm sure there is one, but, sir?
You mentioned that you're pushing in as much air basically as what you can, and I'm just curious what that does to NOx production.
No one that I know has ever done any kind of emissions characterization of one of these. So I'd like to come up with a design which I think actually the gentleman in Sanford, North Carolina, I think actually has a pretty ideal design. I'd like to put that through some sort of a boiler emissions tester, which is actually not that hard to do. They're not that accurate. They don't give you a huge number of different components that they read, but it would be nice to see what that does. I suspect that the kind of propane tank scrap one is not necessarily the ideal. It's just a very easy unit to play with.
Right. That's why I was curious about this. Normally, in combustion, if you limit your excess air, you get lower NOx, but then that causes problems with other things. So
yeah.
What's the trade-offs there?
Generally, like combustion emissions 101 is that generally there are trade-offs between lowering one emissions component and raising another. So because there's such an enormous hysteria about acrolein and about the intermediate compounds that are toxic, that are formed from incompletely burning waste oil, vegetable oil, and its relatives, that's a good one to target.
Posted Bubba what?
Bubba NC, I think is his name on InfoPop.
NC.
If you want to see me privately, I'm sure that he would love to have people email him. He's very friendly. He does not. Anyway, one more thing I want to mention is that there's a whole family of commercially produced waste oil shop heaters that is now starting to be adapted to burning glycerin. Generally, they're talking about mixtures of glycerin and biodiesel or glycerin and vegetable oil. The manufacturers include Ag Solutions, Columbia Boiler, Innovate, and King-Built. And basically everyone that used to make some kind of a waste oil, motor oil burner has realized that there's a huge market for it in small-scale biodiesel production facilities. Price tags are something like $6,000 and up, and I think that's about 150,000 BTU an hour. Is that right?
That would include everything, including your hydronic
Yeah.
heaters and expansion tank, everything.
Usually they quote, most of the other manufacturers quote something in that range. So they're I believe that they're a burner they're an atomizing burner, and then the heat is captured by a surrounding water jacket. Saginaw Valley State University has a little advertised project in which they put a King-Built through its paces and found negligible acrolein production. So that concern is, and they were running glycerin. So that concern really is not that serious. One thing to note about crude glycerin that still contains soap, or unwashed biodiesel that still contains soap, is that you may see increased particulate matter emissions versus burning a fuel that does not contain soap, because the minerals in the soap can't burn by definition. So they form the nucleus of a particle that other stuff attaches to. That's an issue in various petroleum burning situations as well. And there may be that may be a pretty serious concern from a local pollution sort of a standpoint. Generally, the way that in boiler settings, the way that would be dealt with is having a higher smokestack. It basically means you don't want one of these open in your shop, even though it doesn't actually produce a noxious exhaust. You may be aware that there may be stuff in there that you don't see all that well. It doesn't produce like big billowing clouds of anything. And the one other solution to that is to take the soap out in various ways, whether that's ion exchange or some sort of acid splitting up of soap process that probably still would require mechanical removal. That may make it safer to do this from a particulate matter pollution standpoint. John Bush.
Have you done any comparisons of glycerin that's had soap removed versus not?
I've done glycerin comparisons of virtually everything else, so no, I have not. I've run these against, so I've run biodiesel, soap in, and soap out versus vegetable oil versus glycerin, and glycerin with methanol in, methanol gone. And they run, the glycerin one actually starts easier than the vegetable oil one. I'm not sure why that is. The glycerin one will leave behind the most ash. The vegetable oil will leave, or washed biodiesel will leave behind the least. The ash is caused by the mineral content that's in there due to soap, so that's sort of like pretty obvious. But as far as actually testing emissions, it's not that they produce billowing black diesel smoke that you can see, so it's not like not that visual feedback tells you anything.
I'm also just curious about the operation of it.
You turn it on, it starts to swirl, everybody goes, ah! And it's a great party trick. In that kind of open setting, like all the pictures that I showed, it's a great party trick. But capturing heat from it, most people who are playing around with these things are really working with scrap, so they use whatever they've got. The most common use that I've seen where people are actually using it to capture the heat and use it in something practical, they're usually sticking it inside some sort of pre-made jacketed wood stove or jacketed furnace that they have that has water surrounding the combustion chamber. So they're essentially robbing heat from the hot exhaust gases, not from the actual, it's not a direct contact with the flame, but that's usually how they're using it. It would probably be ideal if you had, if we had some sort of good standardized heat exchanger, but I'm not sure that anyone's really put that out on the web.
No question.
John
Sorry.
M.
John and I have talked a lot about cleaning up the glycerol, and you can't heat distill glycerol off because you're going to convert it all to acrolein. So one idea is to vacuum distill it, and you can maybe pull off the methanol first, then pull off the glycerol, leave all the soap and metals behind.
Yeah.
Have you known anything?
I don't know anyone that's done vacuum distillation of glycerol. So what John Muser is alluding to is that unlike a lot of other chemicals that we work with, you can't just distill glycerin at atmospheric pressures to make it into pure glycerin. So our glycerin that comes out of our biodiesel production process is a mixture of different things. They include methanol. We have a pretty easy time getting that out. Includes fats such as biodiesel and any free fatty acids, depending on what you're doing to that glycerol. It'll include a lot of soap. It'll include a little bit of leftover catalyst that is not converted to soap. It will include water, which was made in the biodiesel production process or the soap production process. It'll include anything water soluble or any particulates that were in your restaurant waste oil or other feedstock. So it's a real good argument for why not to use atomizing boilers. Is you've got this fairly dirty product. A lot of the junk that is in our starting oil ends up in our glycerin. So cleaning it up will certainly make it easier to more consistently burn it cleanly. So John is talking about distilling it to actually boil the glycerol and then recondense it to USP type glycerol that you could purchase at lab supply houses. It takes a lot of energy to do that. That would be a boiling point of 660 Fahrenheit for starters. But the other problem is that it decomposes at a temperature that is very close to its boiling point. So essentially, you can't really do it at atmospheric pressure. So the way that it's done is to do the boiling under vacuum. So if you put a liquid under vacuum, you lower its boiling point, that way, but it does not lower the decomposition point at which it begins to decompose into things like acrolein and smolder and so forth. So that gives you more of a latitude of temperatures to play with. So I don't know anyone that's done that, but it's really obvious and logical. I think that it takes a lot of energy still.
I think maybe like a slow distillation, like if you had like a solar panel, just have it slowly.
Yeah, that's the solar panel holy grail. So yeah, we'll maybe next year. That's your assignment for next year.
Okay, we'll work on
So Frank.
I want to hear about ethanol biodiesel.
Yes, I do want to move on. He's actually brought up one of my next topics, which is cleaning up glycerol. Anything else on the Turk burner, real quick?
Just a real quick feedback on the glycerin distillation using vacuum. From what I understand, it requires extreme vacuum. A standard liquid ring pump, which is no inexpensive apparatus, won't even begin to cut it. You've got to go to vein pumps. You're talking 28, 29 inches of vacuum to get there.
Oh yeah, we got those.
There are a lot of pumps that are on the size of your container,
But you can distill metals,
But it's probably more efficient when we can do other things like propane conversion or other kinds of things.
Yeah, there are lots of things that one can do with glycerin, and but I think we've touched on the reasons why they're important, which is that you can't distill it to purify it, and there are many more uses for it if you can actually get it to that pure state. But burning it crude does work. It doesn't really produce immense amounts of obvious pollution, at least in that King-built boiler test that was done up in Michigan. So that's some preliminary data that's really good. Sir?
Would you repeat the names of those manufacturers of that?
King-built, Innovate, which is INNOV, or number 8, Columbia Boiler and Ag Solutions. They're very aggressive in advertising towards biodiesel producers, so it's very, you'll probably get kind of a little bit of an optimistic version from them, but it does appear that they, at least in mixtures with glycerin and biodiesel or glycerin and oil in kind of a 2-tank system, for example, it does appear that they work. So I want to move on to another topic and cover that for a bit. By the way, you guys wanted to start late. Do I have 15 minutes extra?
Yeah, we'll just push for it.
Okay, great, fantastic. Okay, so the next thing I want to talk about real quick is making biodiesel out of ethanol. This is completely mostly unrelated to the glycerin cleanup discussion. I want to touch for a second, actually, before that, on glycerin yet again, because I use it extensively when I make ethanol-based biodiesel. There's starting to be a lot of interest from small-scale producers, from home brewers, in re-examining glycerin as kind of a carrier medium that allows you to do different things in a reaction. And essentially, what we typically do with it is we either use it to force separation in various settings, or we use it to move methanol around, move caustic leftover catalyst around. We use it to remove water. And the way that this applies to ethanol biodiesel is that the main problem with making biodiesel out of ethanol or other higher alcohols is that it's very difficult to get separation of the resulting glycerin. Methanol and glycerin don't, methanol-based biodiesel and glycerin separate relatively readily. They don't really tend to stay mixed that well. But ethanol esters, ethanol-based biodiesel, really does not like to drop out the glycerin that is formed during the reaction. Additionally, ethanol itself, the leftover ethanol alcohol that is in your reaction, that is in your container as a result of using excess to push the reaction forward, is a really good co-solvent. So ethanol is a really great solvent for oil. It's a really great solvent for biodiesel. It's a really great solvent for glycerin. It's a really great solvent for virtually everything we come in contact with. So because in any biodiesel reaction, you're going to use excess alcohol in order to achieve high quality conversion, you're always going to have excess alcohols. With ethanol, it introduces a mechanical separation problem where you might make all the biodiesel and glycerin that you need, but it's very hard to get gravity to separate the two to get, because the leftover ethanol is keeping them is acting as a co-solvent to keep them mixed. So the first thought that people always have is they say, well, let me boil off the ethanol. And then, if I remove the excess ethanol, the glycerin will drop out. Well, the concern about that is that when you start boiling off your excess, it's as if you didn't have any in the first place, and you start reverse reacting. So it kind of undoes a lot of the benefits of using excess alcohol in the first place. So traditionally in the lab, what chemists have done is they've thrown in water after they have achieved conversion, and they've got an unseparating, nice, pretty clear phase that won't drop glycerin and won't float biodiesel. They typically throw in some water. Half the time you end up with a horrible emulsion in that process, and about 90% of the time people give up, and they give away their ethanol and they go back to working with methanol, and they talk about the hit on sustainability that it does. So the interesting thing that happened is about a year and a half ago, I got an email from a school teacher in Maryland who worked with junior high school kids making biodiesel, and for some reason his school district said, methanol is chemicals, we can't handle that, that's very toxic and dangerous, why don't you use E85? Which is, from that perspective is a little bit dumb of them, but he complied, and they basically said, well, ethanol is less dangerous. The only ethanol he could find was E85. E85 is 15% gasoline mixed into ethanol. It doesn't work that well, has some other issues, but that was what he had. So he had to make ethyl esters, and he was doing it he had to make the process work, whether it made quality biodiesel or not. He had the bright idea of throwing in some glycerin that he had, and it forced separation. So that's actually started homebrewers on this enormous tangent of realizing that glycerin is useful in forcing separation in all kinds of different settings, or using it as a carrier to capture various things. So basically in ethyl esters production, it's really taken ethanol biodiesel from being kind of this curiosity in the lab that people wish was more reliable and accurate to being completely practical. because you can, anytime the ethanol biodiesel and its glycerin are not cooperating and you're not getting separation due to co-solvency, if you have some glycerin on hand, preferably from a methanol-based biodiesel reaction, but or otherwise cleaned up, you can always force separation and proceed from there. So I did some work on this in Fiji. Most of the time when people talk about using ethanol biodiesel, they're usually talking about the application being on-farm production of ethanol. That's the big appeal of it. Another appeal of it is environmental. It can be fully renewable, and so it's a very appealing alcohol to use because it really brings up our closed carbon cycle points a little bit. It gets rid of that fossil-based methanol that we typically use when we make biodiesel. Another reason why ethanol biodiesel is useful is that it presumably has a slightly better cold flow cloud point, slightly better cold flow properties. I haven't actually tested to see whether that's the case because it didn't matter where I was making the biodiesel at the time. But you hear all the time from people in developing countries situations where they can't get methanol but have feedstock and various resources available for making their own ethanol, that this would be a very good solution to the fact that they can't make biodiesel due to a lack of methanol and delivery infrastructure for it. So we were in Fiji. Methanol buying was something like $800 a drum, and it required several months of waiting for the drum to come on the slow boat from New Zealand. So it was pretty much impractical. They have lots of waste oil there. They have tourism. They have, American-style waste oil coming off of their tourism. Plus, they have great climate for growing tropical oilseeds, but they weren't able to really they really don't have methanol on the islands. So I went down there on a consulting job for a company that was trying to get into biodiesel production, and they had previously spent a couple of years building an ethanol still. So they had set up a solar-assisted ethanol production process using waste molasses from their local sugarcane plant. So it was actually a very cheap process for them to produce ethanol. They were using Chinese-made evacuated tube solar collectors that achieve very high temperatures, and then a very simple sort of solar hydronic system to provide most of the BTUs for their ethanol distillation. They were using electricity to make that process a little more controllable, but they were able to produce about approximately 99% pure ethanol using a combination of their still, a reflux column, and then zeolite beads in order to dehydrate the ethanol the last few percent. But they weren't doing a very good job making ethanol out of it. So we discovered that there are several issues with this. So you need about something around 28% by volume is approximately the same molar ratio of ethanol to oil as we use when we use 22% methanol by volume. So that's a pretty high amount. You end up with all this excess ethanol. One major problem is that I believe that no backyard tests that exist for testing conversion quality of methanol-based biodiesel work for certain on ethanol-based biodiesel. So we very commonly use what's called the 327 test when we make methanol-based biodiesel. We have a very good, reliable test for checking whether there is unreacted oil or unreacted monodiglycerides. It appears that ethyl esters are too soluble in everything for that to really give a good indication of conversion. So it's absolutely imperative working with ethanol that you use a multi-stage process. So essentially the equivalent of the two-stage base process that we usually use as an 80%, 20% in small-scale biodiesel production. That is very hard to do with ethanol if you can't get separation of your first-stage glycerin, which you often can't. So combining that with the fact that you can use waste glycerin from a previous process to force separation allows you to do two-stage base ethyl esters. So it's, for those who aren't familiar with two-stage base, we typically make your same methanol lime or ethanol catalyst mixture and then use only 80% of it to make kind of a poor quality first stage biodiesel. You're essentially trying to get enough that you're able to make glycerin, get the glycerin out of the way, and then add in your remaining alcohol and catalyst, and that will take your conversion quality much further than if you had done the process with the same amount of reagents and catalyst in one step alone. So I feel like that's a pretty big deal, figuring out a way to reliably get separation. I did a lot of trials trying to figure out whether, what form the glycerin should be in order to force separation with ethyl esters. And one of the things that I found and that other people have found is that if you have water present, it's actually kind of helpful in terms of separation. The big problem is we actually don't know what happens to conversion quality if there's water present, whether the water is in the ethanol to begin with, which is a very common scenario with homemade ethanol. There's very commonly water in it. It's hard to get out completely. Or whether there's water in your feedstock. One interesting thing that I was able to do was work with somewhat higher free fatty acid oil than people typically can do with ethanol. A big challenge with ethyl esters is that usually you really need to work with very high quality oil if you're doing everything, if you're relying on getting reliable separation without any additional work. It appears that the use of glycerin to force separation, the use of previous batch waste glycerin to force separation actually seems to overcome that problem up to a point. I didn't really test what the upper limits are, but I was able to get separation, at least, with homebrew potassium hydroxide based titration of something like 7 or 8, which is really hard to do without having the help of using waste glycerin to force separation. Does that make sense? Okay, Matt.
Just a quick question. One of the concerns that I might have with using the glycerin to force separation would be possible contamination of my biodiesel, for instance with intermediates from the previous batch or something like that, because I guess the way to do that would be to make sure that all of your biodiesel was fully converted, but because there's biodiesel that's going to your glycerin phase, if it's then going back, I would be worried about, because all of my glycerin gets stored and then it gets shipped out, and I would worry about.
So Matt's referring to the fact that when you use your previous glycerin is going to contain biodiesel from a previous batch, unless you do further things to remove that biodiesel, like acidify the glycerin in order to get that biodiesel and oils to float. So generally, if your plant produces high conversion biodiesel, then it does not matter if your next batch is contaminated by high conversion biodiesel.
Yeah.
So I did find that if it is contaminated with ethanol-based biodiesel, it is less reliable as a way to force separation in ethanol-based biodiesel. That was really annoying. Water, at any point, anytime that I had problems, I would pretty much add water as a way to ensure separation. I always did lots of testing on a small scale in order to make sure I had the proportions down to the minimal amount of water needed to force separation. So that's, it really, oh, and one very, very, very important thing that I found about this. Soap numbers are through the roof on unwashed ethanol-based biodiesel. They are typically, I think that we typically see in methanol-based biodiesel, I think we typically see something like 2,000 parts per million of soap on it'll depend on what oil you started with, but it's somewhere around like the 2,000 to 4,000 parts per million range typically when you have not washed your biodiesel. Ethyl esters was 20,000. That's why you get emulsions. So now the reason why this is the case is from what I can tell, and this really affects testing of this stuff. From what I can tell, the extra ethanol, the excess ethanol that is in your ethyl esters, because it is such a great co-solvent for ethyl esters, is holding a lot of your glycerin layer, which would normally rob a bunch of your soap, up in the biodiesel layer. So a couple of problems happen with that. One is that it's very hard to wash. You're going to need a lot more water. You really need heated water. It's a real hassle. So that's something that there are probably other mechanical techniques involving pre-wash. You really need to do a 5% water pre-wash, I'm pretty sure. You need to do something to help bring the soap down, because water washing alone, you're working with a material that is 5 times worse on soap than you're used to. Also, long settling doesn't seem to help, from what I can tell. It doesn't really. Graham-Laming's method probably won't work well, for example. Like waiting for soap to settle or getting soap to cling to a filter is really difficult in this particular situation because of what a good solvent the extra ethanol is. So once again, people always turn to that and they say, well, the solution must be to get rid of the extra ethanol, let's distill it off. I am very worried that because there's so much glycerin with all of the associated catalyst and soap up in the biodiesel layer, I think that you would get reverse reaction much more readily in that situation than what we are used to with methyl esters. So the one solution might be to neutralize catalyst, but I think that there is so much catalyst present at that point that if you were to neutralize it in the biodiesel layer by adding acid, I think you're going to raise your acid number significantly. versus the same exact situation with methyl esters. So that's something to think about, or at least be cautious in proceeding with. So I think really the ways to handle the extra soap there are going to have to be washing with purified glycerol to get soap numbers down, and then wash with water to get all of that, the rest of that out. I think I saw the beginning of questions, sir.
Yeah, I was, here's 2 points.
Uh-huh.
Well, actually, 2 questions. One, ratios. What was the ratio of glycerin necessary to basically force the reaction? And
My big goal was the amount made by the amount made by your previous batch was my goal. That's what I was trying to get to work. Sometimes I added anywhere between 10 and 20% water to that, relative to itself, like relative to the amount of glycerin.
so basically
that always seemed
1-to-1
to
or
help.
excess, basically 1-to-1 of what you'd actually expect to yield.
Yeah, yeah. And I did really careful measurements on what I was seeing, and I was always able to get all of the glycerin I expected by adding extra. So I was able to measure it to, very to like to 5%. So I was able to see.
And then you implied that, in fact, when you stated that you thought that glycerin from a batch made with methanol was better. Did you test methanol, methylated versus demethylated glycerin results? And how did that work out? No, demethylated probably still.
Yeah,
methanol
actually,
is.
I don't remember how it worked out. It was, sorry about that. It didn't really help with, what I was really aiming for was when I had problems getting separation, and I used glycerin made from ethanol-based biodiesel production, which is primarily what we had. Removing the extra ethanol from that glycerin didn't help as much as I hoped. So the problem was the ethyl esters that were in that glycerin. So I think, and I have not gone this far as to test this, I think that you could probably solve that by acidulating your glycerin and getting those ethyl esters out of the way, which is actually my next segment of my talk. Yeah, sir, Steve.
We found that any moisture in the alcohol was a real problem with anhydrous ethanol.
How was it a problem? What did you see?
We wouldn't get separation. If we were
Okay.
using anhydrous ethanol,
Yeah.
we got separation.
See, I found the opposite, and so did a couple of other people. And now, we probably are making poor quality biodiesel when we have wet ethanol. We haven't really tested that. And the reason that it may be a matter of ratios, so like if you had a 1 or 2%, that might make a bigger difference than 10%, which is what I was testing.
Yeah.
And what probably happened is, my guess is that what you saw was that you formed extra soap, and that soap also acted as a co-solvent that helped reduce how much settling you got, is my guess.
Yeah,
But I found that you can always fix that with some combination of glycerin and water.
we were using 33%.
Yeah, okay. Oh, you also had a lot of excess alcohol.
Yeah, and the laboratory grade stuff were great, but we were using
That's
ethanol
$30 a gallon.
denatured with methanol.
Yeah.
And even at a purity level, like in 98%, we weren't able to get separation. And water really made
Yeah.
a horrible emulsion, and even with the glycerin wash, it wasn't pretty.
Yeah, so you had a lot of excess methanol, so that actually inhibited separation. So one other thing that he alluded to, what homebrewers have been doing to deal with ethanol-based biodiesel is that they have traditionally added some methanol to their ethanol and done some kind of a mixture, something along the lines of 4/5 ethanol. So that helps. If you can get any kind of glycerin-based esters in there, that helps force separation. I feel like it's not really necessary as long as you have some kind of post-processing way of forcing separation. The other last really important point I want to make is that I believe that the fact that you can't get all of your glycerin to settle out of your ethyl esters without additional work, I think that it means that enzymatic analysis and other tests for conversion that rely on that give you a total glycerol number, I think they're going to be thrown off by the excess free glycerin that you're starting with. So, one thing that I found is that Greg at Piedmont did some safe testing for me based on a ratio of alcohols that we thought was going to work to achieve high conversion. Had fairly bad conversion in the process. And my suspicion, based on what I saw with soap numbers, is that your standard homebrew visual feedback on how well washed your biodiesel is kind of goes out the window. So I think you need to wash much more than you expect, or you need to do soap tests to ensure that you've actually fully washed. Because just saying, I did three washes of 30% water won't do it. You're starting with 4 or 5 times more soap to begin with than you're used to. So I think that you have to be very careful as far as testing, if you're doing testing by way of any test that gives you total glycerol as the only numbers, the only feedback from the test. Basically because any of those tests, they typically do something like convert all the bound glycerol into free glycerol and then test that result. There's several different tests that sort of work in different ways to do that. I think that they're all going to be thrown off by the fact that you're starting with a lot more than you think, and whatever washing procedures you normally do in order to get rid of the free glycerin for a test, I think are going to be thrown off by the fact that you're starting with so much more than is normal. Ma'am?
Have you done this on a large scale, or are these just like test batches?
It's been test batches. I made ethyl esters before knowing about forcing separation, but it was with really high quality oil, so it really kind of doesn't count. So and it was like ethyl methyl mix, so it doesn't. I don't think of it as really proving anything.
Yeah. And how are you applying the glycerin?
You would feed it in. You would do it the same way that you would. So in any production process where you're doing what we call a 5% water pre-wash, you probably have some way of adding additional material to your reactor and mixing it around, whether that's water or reserved first stage glycerin. So you basically feed it in through your methanol lye delivery system, for example. Usually use a pump. That makes it easier to get it in there and get it distributed. I don't think it matters really. It's not about like residence time of mixing or anything.
Now, are you talking both glycerin pre-wash of your feedstock, then reacting, and then glycerin to force separation?
Yeah, I did that. It helped.
It did help?
Yeah.
Because glycerin pre-wash reduced your FFA
Yeah.
and your oil better?
Yeah. So we were able to do, we had nasty McDonald's oil in a developing country. It was like a 12 or 15 titration. Brought it down to about half by caustic stripping that oil with a batch of glycerin that contained catalyst from a previous batch, and then that put it in the range where it made it possible to make ethyl esters out of it. Whether those were high quality or not, I don't know. So let me take a couple more questions on ethyl esters, and then I want to move on to that a little bit more on that topic. Sir.
Did you use acid esterification for any of your ethyl esters?
In theory, I don't know anyone who's done it. I do know someone who's done it, but it was a very roundabout way, so I don't know.
Does it affect soap levels?
What?
Does it help reduce the amount of soap?
Acid esterification greatly reduces the amount of soap that you deal with in a base catalyzed transesterification. Anyone else? What, sir?
Did you, maybe I missed this, but don't you have to use more also?
Yes. So I think the equivalent. I believe the equivalent is something like 28, or at least the optimal amount that's been found by empirically is something like 28% volume of ethanol. And I think that gives you about the same results in a single stage reaction, I think, as 22% methanol does in a single stage reaction. I think, and this is not my data. I didn't do this with a GC, so I didn't actually I don't know, but I believe that people who have came up with that.
We found that maybe everything I've heard is that the water percentage in the ethanol seems really helping. It's almost impossible to get 100% ethanol. But what we found is that if we took just a little bit of methanol to break down the potassium, that helped a lot because we couldn't get the potassium to break down in the ethanol.
To dissolve, yes. It's also very hard to get your catalyst to dissolve in ethanol. This is true. Yeah, so that's a big issue. And getting methanol does dissolve catalyst a lot better. Okay, next topic. Unless anyone has any other pressing things about. Okay, so next topic: acid catalyzed esterification.
One other question.
Yes.
Sorry. I don't know. Are we supposed to be seeing something?
No,
Okay.
I am looking at my notes. So I'm sorry. No. So it's all in your head. Acid catalyzed esterification. So completely different reaction than making biodiesel by transesterification. So quick show of hands. Who's played with it? Acid catalyzed esterification. Okay. Did you do basically two-stage acid base? Or anyone do anything? I'm sorry?
What is it that you're doing? What are you saying?
Acid catalyzed esterification. Sulfuric acid catalyzed esterification. Okay. So, sir.
I did 3-stage acid base phase.
Woohoo! With two base stages or 2 acid stages?
2 base.
2 base stages, yeah. Cool. Okay, so the process is another, it's another way of getting methyl or ethyl esters. And it does this by reacting, it can react triglycerides, but usually we don't do that with the sulfuric acid catalyst. But most commonly what is done is you react free fatty acids with methanol in the presence of a sulfuric acid catalyst. And the reaction generates methyl esters and water. So it's FFA and methanol, and you need concentrated sulfuric acid, usually like 98%. The exact concentration doesn't matter. It works with like 90%, works with 98%. You know, it might take longer or not go as well with the lower percentages. But it does need to be pretty well concentrated without a lot of water in it. So, so sulfuric acid, and it gives you biodiesel and water. And then usually people then follow that by a regular biodiesel process. So you get, sometimes you get a separation of a water methanol mixture, and you can drain that out, but very often you don't actually see any separation. So essentially this is often used as kind of a pre-treatment step to remove free fatty acids in waste oil or some other setting in which you have them. And it's a process that mechanically the way the process works is you have something like, well, the amount of methanol varies depending on whose process you're following, but in the homebrew method it's usually something like 60% of the amount of methanol that you would normally use being used for your first stage acid catalyzed step. And you add to that a certain amount of sulfuric acid, which is quite minute. Now the process is quite dangerous because mixing sulfuric acid into methanol generates very high boiling temperatures around the droplet of sulfuric acid. The result is that it then tries to come spit at you. And sulfuric acid that touches organic stuff like your skin burns, literally oxidizes it to black ash. And so it's a really dangerous chemical to be playing with unless you have a good way to control for the fact that localized heat will happen. So typically you do it in a stirred reactor. Much of the time when I've played with this, I had a explosion-proof mixer that was mixing in a 55-gallon drum, so I basically just had a mechanical stirrer that was moving the methanol around, and I would drip in my sulfuric acid, and it would be a mostly sealed drum with a vent. So there, any spitting that happened didn't leave the mixer. So it was that's typically how people handle that. Homebrew scale, people sometimes handle that by having a very tall carboy that's only partially full of methanol, and so they're injecting their methanol into a very small hole in the top of the lid. Any local boiling that happens doesn't come out of the container. On a lab scale, you would need to have a way to keep your methanol stirred while you added in sulfuric acid, and once again, a way to keep the container sealed. Do some reading about the dangers of sulfuric acid and how to handle it, because it does introduce a whole nother level of danger. Bunch of hands went up. Sir?
We find that when we mix our sulfuric acid with our methanol, if we simply elevate the pore away from the methanol surface, the weight of the methanol seems to go penetrating into the methanol, and we get way less boiling. Appears to be way safer.
Yeah, just do this in a sealed container. John?
Does it actually work with a kind of a standardized amount of methanol? Because I always like 10 to 20 molar.
Shut up, chemist. yes. He's alluding to the fact that, as many things in home brewing, it would be better to do it a more expensive way.
Based on the titration and just calculate.
Yes. Okay. So let me go there. Let me hold your questions for a minute. Let me just talk about the different ways that this is calculated, that the amounts of all these things are calculated. So what you're going to see is you make a methanol acid mixture. You mix that into your bad oil. Hopefully you have no water in your oil to begin with. This is very important. This is an equilibrium reaction, just like transesterification. So if you have water present, you enable less than complete conversion. So you hinder complete conversion of free fatty acid to biodiesel. And you add your methanol acid mixture into your oil the same exact way as you add methanol caustic catalyst mixture, and then you wait and you wait and you wait and you wait and you mix during that time. And the exact amount of time that everything takes from there on really depends on the amount of methanol you started with and the temperature you're working with and your starting amount of free fatty acids. But something in the ratio I just mentioned, it's something like 12 hours or so before this hits equilibrium. I have found that that time goes way down if you raise the amount of methanol you're working with. So the homebrew holy grail is usually to do the acid-base process without using significantly more methanol than you would do in a single-stage base-only process. The better way to do it is to vary both the amount of acid and the amount of methanol with the free fatty acid content of your oil. The process, the best known process for that seems to be the most reliable is one developed by Dr. John Van Gerpen at Iowa State University at the time. If you do some Google searches, you'll find their papers on that and the exact information.
Can you say the name again? Spell?
Yes, John Van Gerpen. So that, he's got lots and lots and lots of fantastic information out there, but his acid catalyzed esterification or acid catalyzed esterification two-stage method is certainly in a PDF that National Renewable Energy Labs put out. So their method depends on FFA content, and it's I don't know it off the top of my head, so basically it is like for every, oh wait, sorry about that. It's for every gram of sulfuric acid, I'm sorry, for every gram of free fatty acids that you have in your container of oil or fat, which you have to calculate by doing a acid value titration and then calculating percentage from that, or calculating grams from that. For every gram of free fatty acid, you would need 2.5 grams of methanol and 0.05 grams of sulfuric acid. So the problem with that is that for homebrewers is typically we don't work by weight. You usually don't have a reactor with a load cell. You're usually thinking volumes. So there's lots of room for mistakes in that. That comes to quite a bit of methanol. So the worse your oil is, the more methanol you have. You're going to eventually get to the point where you need several times more methanol than the amount of oil that you're esterifying. So it's a pretty, space-intensive process. The thing is that and this will make, the Iowa State University method will do this in 45 minutes. It'll do the esterification that homebrewers need 12 hours or more for in 45 minutes, so under the same conditions. So it's actually very helpful to do something in between. What homebrewers have been playing with lately has been just changing the sulfuric acid based on the titration, based on the free fatty acid content, and trying to keep the methanol quantity within what we consider reasonable. And that is a method there's a method for that was put together by a homebrewer named Dave Kenny out in North Carolina. And the thing that he came up with is to start with a homebrew titration, which is not the same thing as the industry acid value. But the homebrew titration that we're used to, do I have to explain that to anyone? Like what the volumes are? Okay, for every point on a homebrew KOH titration, he'll do the following calculation. He'll take the starting amount. The upper limit seems that this has been tested with seems to be in the 40s or so, like fairly bad oil, but not that bad. And he subtracts an endpoint that he expects to reach, which is usually you don't get any better than 3. So usually he kind of typically just throws like starting titration minus 3 as the standard that he starts with. If you're working with trap grease or something, it's a totally different situation. You're starting with much more. You're not going to get that low in one step, so your endpoint may be higher. So usually it's starting titration minus 3. Then you multiply that times 0.2 grams of 0.2 milliliters of sulfuric acid needed. And the result is going to be the total amount of sulfuric acid needed for every liter of oil. So it's titration minus 3 times 0.2 milliliters. And that is a slow process, and he's adding that to about 60% of the methanol that you would normally use for a single stage biodiesel process. So and what we found is, basically the more methanol you can afford to throw at it, the easier this gets, the faster this gets. I played around with this a bunch of years ago, and I was trying to work on room temperature mixing. This process doesn't need the kind of vigorous mixing that transesterification needs, because it's not prone to separating out your reactive reagents as readily as transesterification tends to. So in transesterification, one of the reasons we have to have very vigorous mixing is that glycerin really likes to separate from your biodiesel and fat and intermediate layer, and it takes methanol and catalyst with it. In this particular case, that's not the case as much. It takes a lot, at least in the homebrew methods, you really don't get separation as easily. So what I found is that if this is a very slow process, you can actually pretty much stir it once in a while. You know, if you can keep it in an insulated container that retains the heat, and it takes 12 hours of mixing. That doesn't necessarily mean that you have to have your reactor tied up using that the entire time. So I was doing, in summertime temperatures, using like 250 gallon batches, and doing it in totes at, you know, summertime, 100 something degree weather. Anyway, that did work moderately well. But this process will go a lot faster if everything is heated high. So the problem becomes what to do when you have water. If you have a high ratio of free fatty acids to oil to start with, you're going to generate more water. The more water you generate, the more likely you are to get a separation at the end of this reaction. You'll see water, methanol, and acid drop out of the reaction mixture. And that process may take a while. It may take up to 12 hours to get all of it to finish settling. It's kind of like letting glycerin settle. So that's an additional wait time on this. This is not a fast procedure generally. You don't always get settling to the bottom. Whether excess methanol goes to the bottom, doesn't go anywhere at all, and stays in the reaction mixture, or flows to the top, depends on how much water is present. So if you started with high FFA, you will make more water. So there's sort of a pretty obvious relationship between FFA and whether you get stuff settling to the bottom. So this will be a pretty acidic mixture, so be careful handling it, but removing it allows you to do this process in 2 stages. So if you wanted to get further conversion, for example, if you had very bad quality trap grease, you'll need to do this in multiple stages, and you'll need to do something to force separation of the water that is formed. Generally, you can kind of manage that by managing the amount of methanol that you're working with. So for instance, if you have more methanol, it'll be less prone to dropping water-methanol mixture to the bottom, I believe. So there's like methanol management techniques that can be used in this. I have not played with those personally. Greg had a hand.
Yeah, I may be wrong. I'm not sure about this, but I think we need parentheses around the titration 3. Is that right? Yeah. You don't want to do 3 times 20.
Yeah, sorry.
Because in case people write it down.
So,
I was wondering if anybody's ever taken the water from the bottom of this and combined it with maybe the wash water from acid base neutralizing.
Yeah, it'll be acidic water. So the idea that I haven't had a chance to play with recently is I was thinking, take that dropped out stuff and use it to acidulate your next glycerin. If you then do methanol recovery, you haven't lost the methanol. It hasn't been tried. The process goes much better if you really dry your oil out really well. So that seems like that's really crucial. That's another really big drawback of working with high FFA oils, is that you have to spend a lot of effort on getting, generally high free fatty acid and water contamination generally go together. Sometimes you get water contamination but not high free fatty acids, but usually it's the other way around. They're almost always together. So that's a big problem. Like, you really have to ensure that you're water free. So a couple of hands that.
Yeah, I'm doing a lot of work with crude oil and running into the problem of degamming and phospholipase. And I was wondering, this process is very similar to the super degamming method that you get minus the methanol at the beginning. I was wondering if you did acid esterification and drained it out, that would essentially work to remove those phospholipids also?
I don't know the answer to that, but so I can't tell you. Sir.
I guess I just want to make sure I'm not as familiar with acid esterification as maybe some other people. On this reaction, if we were doing this with waste veg oil and a traditional biodiesel processing, would we have waste veg oil on both sides of this reaction?
Yes, this is all happening in a matrix of oil.
Right, so I mean, I've got oil over
this
here
process
with
doesn't
high
really,
free fatty acid content.
Yeah, so at the end, what you're going to end up is biodiesel in waste vegetable oil. So the second stage of this is to take your remaining methanol and transesterify the oils that all this free fatty acid was in.
So I turn my fatty acid into biodiesel,
Yeah.
and take the rest of the oil.
And turn it into biodiesel, and you'll get glycerin that time around. So one thing about that is that if you have drained off a methanol water acid mixture, then you may need to add extra methanol in order to compensate for the fact that you removed some methanol. Now, here's where it gets interesting. I have found that looking at data on anyone homebrewing who has been doing conversion testing, and this is a bunch of the you BioPro guys, people seem to typically get better results with their conversion than you would expect. So so basically this process, what you're going to see is you'll see the titration numbers go down. So you'll get down to something like 3 from something like 40. You know, like you'll take really awful oil and put it more in the range of what only lightly used waste oil is like. But it still looks, from what I have seen numbers-wise, it looks like people for some reason also get better conversion. And I am very interested in the issue of why. And I think that what's happening is that I think that in your base stage, your second stage transesterification, I think the biodiesel helps in marginal mixing environments. So if you have a oversized apple seed or some kind of a not very good mixer, I think that having some extra biodiesel acts as a co-solvent. There's lots of ways to test this. Do transesterification, then do another batch with the same oil but add some biodiesel. Does that help? I think that's all I can think of that would explain that, unless this process is also transesterifying some triglycerides, some oil, into biodiesel, which it will do. It's just a much slower process, so we typically think that it doesn't happen.
Isn't that part of the way?
I'm sorry, go ahead.
Isn't that part of the reason that 80-20 works?
That's different. So 80-20 is overcoming the equilibrium issues.
No, I understand that, but I mean, by the time you get a little bit more esters in there, the solvent.
That's part of 80-20. Yeah, that's part of what makes 80-20 work, but it really is equilibrium. It's the fact that you've gotten the glycerin out of the way that would otherwise interfere with full conversion grade.
So is this assuming 60% of the normal methanol you'd use
in
then?
the first stage, 40%
Okay.
in the second stage, or plus whatever you may have drained off, compensated for by adding extra methanol. So typically, what in the kind of more homebrew range of what people see when they're working, usually homebrewers aren't working with trapperies. You're usually working with like a maximum of like 25 titration. Homebrew titration oil. Usually it's not much worse than that. Sometimes it might be, but usually it's not that bad. So that's not this is a very good candidate. This recipe is a kind of a very good formula for working with stuff in that range. When you start working with trapperies, you start working with really dreadful, terrible oils, you wind up with more problems with this kind of Dave Kenny sort of formula. You may need to look up what John Van Gerpen did and adapt it to your equipment. But the amount of methanol that, trying to keep the amount of methanol the same does seem to work with that kind of range. And typically what we are seeing is maybe half of the methanol that you used in your first stage, maybe the volume of about half the methanol is what you see drop out. You can calculate how much water it'll form. If you know that you started with no water in your methanol and you know that you started with almost no water in your oil, you can pretty much calculate the volume of water you expect to see. But so you can pretty much calculate how much methanol you would need to add to your second stage to make up for any that you drained in your acid stage.
You
Sure.
compensate with adding more KOH to neutralize the...
You would, at the end of this process, at any of these processes, at the end of, no matter whose formula you're using, you titrate, and you titrate, and you titrate. That's what tells you that the process has gone to completion, is that you don't see the acid value go down any further. But what you will see is that there is some acid in there, and that is either fatty acids or sulfuric acid, and adding KOH in calculating the amount of caustic the completely normal way that you would normally use for transesterification will take care of that. So what you will form is salts based on which catalyst you used with your sulfuric acid. You'll form a salt that is water soluble and can be washed out.
But your titration is going to be, there's going to be some error in there because of that sulfuric.
Yes, but it doesn't matter because your catalyst will neutralize it and then it does not interfere with the transesterification reaction. So that's, Matt.
Yeah, well, you say that you probably will only get down to a titration number of 3, for instance, or something like that.
Yeah.
Is part of that's going to be the mineral
Sulfuric acid, yeah. Now, if you had, if a layer of something floated or sank, that'll have a lot of that acid.
Right. And I guess. Okay, right. But
Okay.
I guess my point is that you might be a reason that you're getting a really good yield would be that it's actually a better titration than you. I mean, less FFAs than it actually indicates.
Yeah, sure. But I mean, I typically in California work with like 0.5 titration rice oil, and it's. But I can't get very good results with it. Neither can Andrew Morris, actually, for some reason, who has a different source of the same oil. There's something up with that. But anyway, we can't get the same kind of good results that people who are starting with worse oil and doing acid base are getting. in like Appleseed reactors. So it's same exact equipment. So it's obviously, there's obviously something to this that helps with conversion from what I can tell. So I want to move on. Are the organizers here? Do I have 10 more minutes?
You got about 5 more minutes.
5 more minutes. Okay, great. Let me move on. I'm not taking any more questions unless they're desperate. Okay, now I would like to introduce the base backwards two-stage method. Real quick, there's a, so I'm cutting out a little bit of stuff I wanted to cover, but we generate lots of soap. A lot of it goes into the glycerin, a lot of it is in the biodiesel, depending on whether you do the 5% water pre-wash at the end of your transesterification, which in short is add 5% by volume water compared to the amount of oil you started with to your reactor before you have drained the glycerin. This part is very important. Before you have drained the glycerin, then remix everything back into one phase and let it separate, which will then put a lot more of your soap into the glycerin than you would normally have had in your, that normally would have stayed in your biodiesel. That will really change the amount of soap in your glycerin. You'll end up with a whole lot more in there than normal. Anyway, so there's soap in one place or the other or both. Where there are various ways of chemically handling that soap. One of them is various kinds of ion exchange methods. So for getting soap out of biodiesel, people are now running biodiesel through ion exchange resin to try to capture it. Glycerin has lots of soap, and as I mentioned in the boiler discussion, soap can be a problem in the glycerin because it, if you're going to burn your glycerin byproduct for heat, because it can be the basis of particulate matter emissions, and it forms lots of ash that forms a sludge in your burner, which is also more immediately troublesome. One very basic chemical process for purifying the glycerin byproduct that lots of people know about is to add various kinds of acids to your glycerin byproduct in order to break up the soap into two of its component parts, which are fatty acids and salt. Those are the products that you get when you perform that reaction. So the acceptable acids to use are hydrochloric acid, which is very cheap, but it's a little bit noxious, and it gives you salts that don't separate out very well. Sulfuric acid, which is, as I mentioned, has the problem of boiling when it hits an alcohol or water, so be careful with that. Or phosphoric acid, which is deadly expensive and gives you all these like phosphates that, depending on any agricultural purposes, any agricultural uses you're using your glycerin for, you may not want to use phosphoric acid under some conditions. Anyway, so sulfuric acid is kind of what I think is probably the best one to use. Adding acid to soap breaks up the soap into free fatty acids and salts. Two other things happen in our case. So soap is going to hold oils in a matrix in it. So generally in a glycerin layer that results from making biodiesel, you will have lots of soap and you will have a whole bunch of biodiesel. And it's actually shocking how much biodiesel there is trapped in your glycerin. And the soap was formed from the free fatty acids that were in the oil that you started with. So whether you did esterification or not, every time you do transesterification, any free fatty acids and a few that are kind of split up during the reaction combine to make, with some of the lye, to make soap. So acidulating gives you a way to turn that soap into an oily layer, which will include any trapped biodiesel, as well as salts, which will dissolve either in the oily layer or the aqueous layer that you get. And the aqueous layer is going to be where your actual glycerin goes, along with anything water-soluble and any water that was formed in these reactions. So you'll get a mixture of water and glycerin that is a lot more usable for various processes, such as animal feed, cosmetic, soap, cleaners and stuff like that. And then you'll get a layer of oils. Well, the layer of oils is going to be at least half the volume of the full amount of glycerin that you started with. So people acidulate so that they can get usable glycerin, but they always have this kind of like waste product of very high FFA oil that they don't know what to do with. I did a bunch of tests with it last week, and I found that I found that it esterifies a lot more easily than the equivalent amount of free fatty acid in oil. Again, I think co-solvency is what's going on, because this is biodiesel with free fatty acids. So I did, in one step, I went from 55 titration down to 3, what did I say? It was like very minimal. That used quite a bit of methanol. I've repeated this another time. You know, it was a lot of methanol, but it gave me quite a bit of the methanol water layer to that potentially recover methanol from. But it did it. It converted that 55 titration stuff to 3, like very completely. I would not have expected Dave Kenny's method to do that with the equivalent bad oil. If I had triglycerides with that much free fatty acid, it would not have gone that low in one step. So the process passed the stuff passed the 327 test. So and I got quite a bit of it. You know, there's quite a bit of it that came out of my sample of glycerin. It was over half of the amount of oils that I had to work with was over half the amount of glycerin that I started with. So all of you that are stockpiling glycerin in your backyard probably have a little bit of a source of feedstock there for making biodiesel out of, or at least recovering the already made biodiesel out of that you've already spent money on. So it reminds me of the fact that I have read about some laboratory research where researchers, again at Saginaw Valley State University, they were working with trap grease and they made ethyl esters out of trap grease, which is like unheard of. They were completely matter-of-fact about it, like, oh yeah, of course. And you know, they were working on a lab scale as well. What they did was saponify the trap grease and then use acid to break up the soap. In the case of trap grease, the reason that they did that is that they needed to sterilize the trap grease because of all the bacteria that are very toxic to humans that are in it. So that was one of the reasons they took that step. But they then got 100% FFA or something like that, and that appears to be very easy to esterify relative to working with triglycerides and FFA, from what I can tell. The final notes that are great just called time. Final note on that is when you split up soap that is in a matrix of glycerin, which is the case in the case of glycerin byproduct, once again, glycerin grabs water. It's kind of one of those situations where glycerin is a carrier for aqueous substances. So glycerin will actually, I think that one of the things that helped me in the couple of tests that I've done is I think that the glycerin gave me a very, very, very dry feedstock to work with for esterification, and I think that helped greatly. So I see an innumerable number of ways to apply this if it actually does scale up, if it actually does what I think I saw, because I've really done all of 2 samples. So this it makes a lot of sense from a theoretical standpoint. So I encourage you to try it out.